Welcome, ladies and gentlemen. My name is Andreas Holzinger. This is our 10 minutes presentation plus 5 minutes discussion of paper 139, Classification and Visualization of Patterns in Medical Images. Let us start with the question on how human pathologists make diagnoses. So, pathologists look at such histopathological images. They follow in principle the famous Schneiderman paradigm. Overview first, then zoom and filter on demand. And they use medical terms, which includes biological phenomena, for example, cells, tissue types, anatomical elements, and abstract patterns. They speak about an architecture, a penetration, distribution, differentiation, grading. Here, for example, is a portal field, and so on. So basically, they form descriptions and interpret it with their implicit human knowledge. Cells are smaller and closer together. It is a tumor. But this can also be an inflammation. It depends on the context. It is important to note generally that in the medical domain, different modalities contribute to one single medical result. So, current AI is very successful in object recognition, in quantification, and can also perform complex classification tasks. So current medical AI is already able to reach human level performance. Here, a very recent work from the Princess Margaret Cancer Center in Toronto on histopathology. They applied CNN to a repository of 840,000 histopathological image tiles and learned representations into a 512-dimensional feature vector. The novelty here is that they compare with human constructs. They demonstrated that individual machine-engineered features correlate with salient human-derived morphologic constructs and ontological relationships. This is an important next step in an overlap between human and AI interfacing, because it can help to eliminate biases and improve the accountability for future AI-assisted medicine. So this is really awesome work, and of course we are proud that they pointed to our work on causality, which I will discuss later. Generally, there is no doubt that AI has great potential for medicine. So, what is our story? So, fact, medical AI is currently extremely successful and can reach human level performance. However, in the real world, we are facing 3 challenges where we want to contribute with this ongoing work. First, ground truth is not always well defined, especially when making a medical diagnosis. Second, human scientific models are often based on understanding causal mechanisms. And third, successful machine learning today is typically based on correlation or related concepts of similarity and distance. So, among others, this was the motivation for the development of our KandinskyPatterns exploration environment, which I will show you in the next slide. So, #KandinskyPatterns, within our exploration environment, we are able to build such concepts as you have seen before, but along with the ground truth. Here, for example, the cells are smaller and closer together. It is a tumor. But we can at the same time produce completely false patterns. For example, here a complete random pattern. But, and this is the most important, we can also produce counterfactuals. These are causal models which allow to ask and to answer counterfactual questions. For example, what if the cells are slightly bigger? A big advantage of this counterfactual generation is that this can be considered as a post hoc explanation procedure which can act independent from any classifier. So this is a very central work in explainable AI. And here our Kandinsky patterns are extremely helpful because this enables us to study causality the art and science of cause and effect. So causality is the effectiveness that connects the cause with the effect. Causality can be seen as a relationship between one process or state to another process or state, and this is a fundamental principle of all natural science, yet this is science per se. We have extended this concept and introduced causability as the measure of the extent to which an explanation of a statement received from an explainable AI method, for example, receive an outcome from, for example, layer-wise relevance propagation, where the most relevant parts which contributed to one result are highlighted via heat map. So we can extend this statement to a human user to achieve a specified level of causal understanding. So the measurement criteria include effectiveness, efficiency and satisfaction in a specified context of use. And remember what I have said before, the context of use is always very, very important. And mapping, by the way, comes from cartography. And this mapping is central for us and brings us now to the key point, to understand how shapes can be explained. So, luckily, our world is compositional, as Jan LeCun always emphasizes, and therefore we can make use of so-called shape grammars. When recognizing compound structures, we can make use of either Gestalt laws and the work of Jacques Berthoud. Jacques Berthoud proposed a set of visual variables, for example, position, size, shape, value, hue, orientation, texture. But there's more. There's also, in addition to these shape categories, there are so-called silhouette attributes. And this is in particular important for histopathology because these describe the outer form of a shape. For example, here a tubular shape, a squamous, columnar, symmetrical, or asymmetrical. And moreover, there are inner structures, for example, a point, for example, a random, for example here, random inner structure, or a aligned or rastered inner structure, or a mixed inner structure, or an adjacent inner structure, or a circular inner structure, and so on. And such structures are observed as recurring patterns in histopathology. And here graph theory can be of great help. The computed graphs, for example, can be processed then via graph neural networks, which are currently en vogue, to further enhance graph extraction by improved node classification, and we can do link prediction, for example. So graph explainability is an upcoming, very important research topic which will help us for explainability. So in conclusion, we work currently on generating a catalogue of shape concepts to be used in natural language descriptions and AI dialogue systems. Within such a controlled vocabulary, terms such as well-differentiated can be mapped to a specific technical feature in AI-based classification. So, with the help of our KandinskyPatterns exploration environment, we can generate large training sets of shape patterns together with natural language and annotations. And this can be used for training networks to classify various concepts. So generally, we can measure, or we want to measure as an outcome, measure the quality of explanations with effectiveness, efficiency and satisfaction in the specified context of use. And we have chosen the term causability in reference to the well-known word usability. And it is again important to note that in medicine, many different data contribute to one single result. Thank you very much.